Okay. All right. So we are being recorded now. Um, so okay. So what I want to do is I want to remind people that there is an office hour on Monday at 11 to 1. And my grader has just told me that she has all the homework graded. So you can pick up your homework at that time. Okay. This other announcement I wanted to make was there are other YouTube videos available for review that I listed in an earlier email. So if you want to review material from the first two thirds of the class, then you can do that by going to the YouTube channel. Okay. Are there any questions at this time? Okay, so the first thing I'd like to do is I'd like to start off by giving you some definitions. Okay, so these are definitions that you should know by heart and that you may have to use. And remember, in this class, you always get points for knowing definitions. So you may not be able to solve the problem completely, but if at least you know the definition, you will get partial credit. Okay, so the first definition is the definition of linear independence, which we've gone over many times. Okay, so you take a bunch of vectors, you want to actually say when they're linearly independent. You want to also know when vectors actually span a subspace. Okay, and then with linear independence and spanning, we have the notion of a basis. So you should know what a basis is. So a basis for a subspace is just a set of vectors which is both linearly independent and spans a subspace. Okay. You should also know what a subspace is. So I'd actually like to go over that definition right now. Okay, so we haven't used it too much, but I want to actually go over this. So let W be a subset of Rn. Then W is a subspace if and only if, well, first of all, the zero vector has to be inside of W. Okay. What else has to be true? Well, if I take two things in W, then their sum has to be in W. And then three, if we have a scalar and a vector in W, then the scalar times the vector has to be in W. Okay, so in other words, a subspace is basically closed under vector addition and also scalar multiplication. Okay, that's actually good enough, but for just for the sake of completeness, we just say the zero vector is also inside of W too. W also. Okay. Um, you should know what a determinant is. And you should know what a linear transformation is. Okay, we've gone over that before. You should know what it means to be an inverse of a matrix. Um, And then these are from the earlier parts. You should know what the null space is. Okay, so the null space is just a set of homogeneous solutions. So it's a set of all vectors in Rn such that A times V is actually equal to the zero vector. Okay. You should know what the column space is. So it's a span of the columns of a matrix. You should know what the rank is of a matrix A. And you should also know what the dimension of a subspace is. Okay, so the dimension, of course, is the number of elements in a basis for the subspace. Okay, and then a few more. Um, so you should know the definition of an eigenvalue and an eigenvector. So the idea is if you have A times V is equal to lambda times V, where V is not equal to zero, then lambda is an eigenvalue and V is an eigenvector. All right. Now, let me just pause for a second. Are there any questions on these definitions? Hang on. I got two more to admit here.
Excuse me?
Yeah, go ahead.
Sorry, I was just wondering, do we need to know the definition of a determinant or just how to calculate it?
You should probably know the definition in terms of being able to expand it out, but let me just say, more likely you'll have to know how to calculate it.
Okay, sounds good. Thank you.
Okay. But things like basis, so let me actually put star. So this one you definitely should know by heart. Okay. So these, let me put the little stars by them here. Okay, determinant, maybe not. Linear transformation, yes. Inverse, yeah, you should probably know what that is. Null space, column space, rank, dimension, yes. And then eigenvalue and eigenvector. Okay. All right, other questions? Okay, so let's move on. Okay, so now we're going to start with the last third of the class. So the first topic I want to cover is eigenvectors and eigenvalues. Okay. All right. So the way the story starts is you start with the square matrix. So A is an m by n matrix. Okay. And then we look at a certain equation. So the equation is AV is equal to lambda V. Okay. And V is not equal to zero. So as I mentioned before, V is what's called an eigenvector, and lambda is an eigenvalue for A. Okay. And V is an eigenvector with corresponding eigenvalue lambda. Okay. Now, how do you actually compute eigenvalues and how do you compute eigenvectors? Okay, so to compute an eigenvalue, recall you use the characteristic polynomial. So to do eigenvalues, you look at PA of lambda, which is the determinant of A minus lambda times I. Okay, so remember this is a polynomial on lambda of degree n. Okay, and the eigenvalues are just going to be the roots of the characteristic polynomial. Whoops, I got more people coming in. Sorry. Pause, pause. Okay. All right, more people joining. All right. So the eigenvalues, whoop, sorry, are the roots of PA of lambda. Okay, so we've done this many, many times. We've computed eigenvalues for matrix A by doing this, finding the roots of the characteristic polynomial. Okay, so how about eigenvectors? So once you actually have an eigenvalue, you can actually find all the eigenvectors. So given lambda and eigenvalue, you can look at V lambda, which is the null space of A minus lambda I. Okay, so this is a subspace of Rn, and this is called the eigenspace. Okay, and and the non-zero vectors in V lambda are the eigenvectors for corresponding to lambda. So the non-zero vectors in V lambda are the eigenvectors of A corresponding to lambda. Okay, and we know how to compute the null space. It's just going to be, you just use Gaussian elimination. So the null space, you're looking at the homogeneous system of equations and you just compute out, the solutions for the homogeneous system for A minus lambda I. Okay, and we've done that many, many times. All right, any questions on this? Okay, so why are eigenvalues and eigenvectors important? Well, they're important because we can actually show that A is similar to a diagonal matrix under certain conditions. Okay, so there's an important notion of diagonalization. Okay, so A is diagonalizable if and only if A is equal to P D P inverse, where D is a diagonal matrix. Okay. All right, so that's the definition. So you want A to be similar to a diagonal matrix. Now, this doesn't always happen. So the condition that ensures that this happens is if you take the sum of the eigenspaces and the sum of the dimensions is actually equal to n. So remember the theorem. So A is diagonalizable if and only if when you take the sum over all the eigenvalues of the dimension of these eigenspaces, you get n. Okay, so you compute all the eigenvalues for A, you compute all the eigenspaces, using Gaussian elimination. You sum the dimensions. If it's equal to n, you know A is diagonalizable. If it's not equal to n, if it's smaller than n, A is not diagonalizable. Okay, is that clear? All right. Now, the nice thing about this formula over here is that it's related to the eigenvalues and eigenvectors for A. Okay. So if A is diagonalizable, then our D consists of, oops, sorry, I have another admit here. Okay. All right, here we go. All right, so it consists of eigenvalues down the diagonal. Okay, so these are eigenvalues of A. And then the P will consist of eigenvectors corresponding to each eigenvalue. So these are the eigenvectors. Okay. All right. So I have a sample problem for you to try at home. Okay. So here's a sample problem. Okay. Which you should work out on your own. Okay. So let A be equal to the following matrix. Okay, so I have 4, 0, minus 2, 2, 5, 4, and 0, 0, 5. Okay, so find an invertible matrix P and a diagonal matrix D such that A is equal to P D P inverse. Okay, so basically you want to show that A is diagonalizable. Okay, so of course, in order to do that, you have to find the eigenvalues, find the eigenvectors, and then, put things in the right form. Okay, so this is a good exercise for preparing for the final exam. Okay, so let me pause for a second. Are there any questions on this? Okay, so let's continue on. So another application um, is the idea of taking powers of matrices. So if you know something is diagonalizable, you can actually find the power of a matrix pretty easily. So suppose you want to find A to the 100th power, and A is equal to PDP inverse. Okay. So then when you take A to the 100th power, that turns out to be equal to P D to the 100th power P inverse. Okay, so all you have to do is raise the entries in the diagonals just to the 100th power and multiply it by P and P inverse on both sides. Okay, so you could actually take powers very easily if you know that A is diagonalizable. Okay, so you should know how to do that. The second application was the application involving difference equations. Okay. So we did several examples of this. We actually found a formula for the Fibonacci numbers by using a difference equation. We had an economic model where we looked at what happens in the long run with a certain difference equation. And we also looked at predator-prey models. All right. So you should be, you should actually study the predator-prey examples. And then we had the economic systems. So I think we have that in our notes. And then we also had the Fibonacci series. Okay. And the idea was fairly simple in many ways because, we just assume that we have diagonalizability. So the difference equation looks something like this. So at the k plus first stage, you have a times x to the k, okay? And a is an m by n matrix. Okay, so the kth stage or the k plus first stage is just obtained by taking the kth stage and multiplying by a. All right, so when you do that, well, let's just do some examples. So x1 is going to be equal to a times x0. X2 is going to be equal to what? A times x1, which is the same as a squared times x0. So in general, x to the k is equal to a to the k times x0. Okay, so in solving a difference equation, you just have to take a to a high enough power. And so we actually found a formula for this. So there's a formula, and it was given as follows. So let's say A is diagonalizable. Okay. And lambda 1 up to lambda n are the eigenvalues. Okay. And then we have corresponding eigenvectors. Okay. So then I can write the initial condition x0 as C1 V1 plus Cn Vn, okay, for some C's. Another way to say this is that x0 is equal to the matrix P times um, C1 up to Cn. Okay, that's another way to say that. And so then if I want to find x to the k, this was going to be C1 lambda 1 to the k times V1 plus Cn lambda n to the k times Vn. Okay, so if you know that A is diagonalizable, um, then you can actually find out what x to the k is by just using the eigenvalues and the eigenvectors. Okay, so given an initial value, you can find the c's using the eigenvectors, and then, off you go. You can actually find this nice expression. Okay, again, let me pause for a second. Are there any questions on this? Okay, so the next thing I want to talk about is orthogonality. So this is, I guess, number.
Excuse me, Dr. Nakano.
Yeah, go ahead, Arjun.
Uh, By chance, could you do an example on the concept we just covered, the difference equation, please?
I won't have time during this review session. I think that we did some examples. Uh, we did some examples in class.
Okay,
So
that's
I would look back at the notes.
all right. Sounds good.
I think we
Thank you.
did like 3 or 4 examples where we actually used this.
Okay, sounds good.
Okay.
All right.
Yeah, I need to cover quite a bit during this review session. So,
I understand. Thank you.
okay. All right. So the next topic is orthogonality. Okay. All right. So in order to understand orthogonality, we have to have various tools. And the tools involve using the inner product and, for example, the length, right? So if I take two vectors, u and v, I can define the dot product as u transpose v, which is u1 v1 plus un vn. Okay, you take the sum, you take the product of the components, the corresponding components, and then you sum them up. Okay? And if I want to know the length of v, of course, this is the square root of v1 squared plus vn squared. Okay? And of course, if you take the dot product of v and v, you get the square of the length. Okay, I think that's pretty clear. Now, if you take two vectors, u and v, these are orthogonal if and only if u times v is actually equal to 0. Okay, the dot product is actually equal to 0. And then you can extend this to actually sets. So a set u1, u2, up to u sub n is orthogonal. Let me do it this way. Orthogonal if and only if ui dot uj is 0 for I not equal to j. Okay, so basically, if you look at different vectors in that set, you want them to be perpendicular to one another. And then if you want them to be orthonormal, you have to have orthogonal and you have to have length 1. So it's orthonormal if and only if the set is orthogonal and the length of uj's are equal to 1 for all j. Okay, any questions on this? Okay, so here are things that you should know how to do. Know how to, 1. So you should be able to determine whether a set is orthogonal or orthonormal. Determine if a set of vectors is orthogonal or orthonormal. Okay. So you have to take inner products and then for orthonormal you better check the lengths. Okay. 2, given an orthogonal set, you should know how to make it an orthonormal set. Okay, so let me just kind of review that really quickly. So you have your orthogonal set of vectors, so the inner products are all going to be zero between any two of them. Now, to make an orthogonal set, what should we do? Orthonormal set, what should we do?
Divide by the unit vector.
So we want to divide by the length, right? So we divide the vectors by the length, and then that produces a unit vector. Okay? So we've done that a lot in class. All right. Now, the next important concept we had was the concept of orthogonal projection. So let me list that as 3. And the reason why we want to talk about orthogonal projections is because sorry, we're able to apply the Gram-Schmidt orthogonalization process to vectors. Okay. Wait. Oh, I lost everything here. Darn it. Okay. All right. I'll tell you what. Uh, I hope maybe some people are taking some notes. What I'll do is I'm going to post these notes on ELC. Okay. So what I'll do is I'll fill in this orthogonality part before I post the notes. Okay, fair enough? Yes? Okay. I hope that's good enough. So I'm going to leave. I actually can put space in between this, so that's not a problem. So I'm just going to move on to orthogonal projections. I don't know why this didn't say. So, so I'll fill this in before I post it, okay? So orthogonal projections. Okay. All right. So here is the idea. So the idea is you have a subspace W, and the idea is you have an orthonormal basis. Actually, just an orthogonal basis. So let U1, U2 up to U sub t be an orthogonal basis for W. Okay? And so the idea is when you take a vector outside of W, call it Y, then what you can do is you can project the vector down, and you can actually write it as something in W and something orthogonal to W. So this is Y hat and this is Z. Okay. So for every Y in Rn, Y is going to be equal to Y hat plus Z, where Y hat is in W and Z is perpendicular to W. Okay, so this was the orthogonal decomposition theorem. And the orthogonal decomposition is unique. So there's only one way to do this. Now, the nice thing about having an orthogonal basis for W is I can write out what the projection is by using this basis. So there's an explicit formula for the projection. So this is called projection onto W of Y. And this is given by Y on U1, the dot product, over U1, U1 of U1, the dot product of Y on U2, 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 of U2 plus you take the inner product of y with UT, 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 and UT. Okay, so there's an explicit formula for finding out what the projection is with an orthogonal basis. Okay, good. So now what we can do is we can apply this projection idea to describe the Gram-Schmidt process. All right, so what's the Gram-Schmidt process? The Gram-Schmidt process is if I take any basis for a subspace in W, then I can use orthogonal projections to straighten the basis out and make it an orthogonal basis, right? So um, let me call them x1, x1 up to x sub t be a basis for the subspace W. Okay, so here's how it goes. So then I'm going to set the first basis vector to be just x1. Okay, and then what I do for the second basis vector is I take x2 and then I subtract off the projection. So x2 v1, 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 the inner product times v1. Okay? And then the next one, what I do is I take x3 and then I subtract off the projection from that. Sorry, let me erase this, make it a little bit cleaner. Okay, so then what do? I take x3 v1 v1 times v1 minus x3 v2 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 on the vector v2. Okay, and then you could see what you do. So the final step, so dot dot dot. So at the end, the last vector, you're going to take x of t, and then you're going to subtract off the projection. So minus um, xt v1 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 on v1 minus xt vt minus 1 vt minus 1 dot vt minus 1 on vt minus 1. Okay, so these are vectors and the other ones are inner products. Okay, so once you do that, then the v's are orthogonal. So then v1, v2 up to vt is an orthogonal basis for W. Okay, so that's what the Gram-Schmidt process allows you to do. Okay, any questions on this?
Wait, I have a question.
Oh, go ahead, Daniel.
When you're doing like the x3 minus and then all that stuff, v1, v2 and all that, does it
Yeah.
matter what order, like if you do the third term before the second term, or is it okay to like do them last to first? Like do you see what I'm saying? Like v1 last, or should v1 always be the first thing you subtract?
Well, I mean, if you take, if you permute the basis elements, like, then you could still apply the process and get orthogonal basis. But you make it in a different ortho. Well, actually, let me think for a second. Yeah, I think you might get a different orthogonal basis. I think it depends on what order you actually do things in.
Okay, okay, thank you.
Right. Yeah, of course it does, because I mean, the first one you actually pick the actual vector, you know. So if I, for example, reordered this and I started with x2, see, then your basis would be different. It'd be sort of oriented relative to the second vector instead of the first vector. So it's a good question. Okay, other questions? All right, so so now let's talk about least squares. Okay, so let's see, 2, 3, 4. All right. Okay. So, we've always been interested in understanding um, the solutions of AX equals B. Now, sometimes we don't have any solution, but what we can do is we can ask, is there a best possible solution? So, if I look at the column space of A, so these are the things of the form A times X. And let's say B is not in the column space. So if B is not in the column space, then it's going to sit outside, and there's no X for which AX is actually equal to B. But what we can do is we could try to minimize the distance from B to the column space. Okay, so that's the idea. So here's A times X over here, and we want to minimize the distance. So if I take E to be equal to the set of all AX minus B's, and we want to minimize this. And a solution which minimizes the error is called a least square solution. So if X minimizes E, then X is a least squares solution. Now, what we did was we sort of analyzed what the possible least square solutions are. So first of all, least square solutions have to satisfy the following equation. So A transpose A times X is equal to A transpose B. Okay, so we did some analysis on this, and we actually figured out, yeah, if you have a least square solution, then this equation has to be satisfied. Now, what we want to do is we want to be able to invert A transpose A, because A transpose A is just a square matrix. So the condition which allows us to say when A transpose A is invertible is if A has linearly independent columns. So if A has linearly independent columns, then the least square solution is unique, and you can write it as A transpose A inverse A transpose B. So this is unique now. Okay? And the point which is closest to B is A times X. And and that's going to be equal to A times the whole thing. Okay, so this is the point closest to B. Okay. All right, so the obvious thing or obvious problem that you should be able to solve is you should know how to solve least squares. Okay, so if I give you a matrix A and I give you a B, then you should be able to find all the least square solutions just using this method. Okay, so one application we had was the application of data fitting. Yeah, so I wouldn't worry about generalized linear models too much. Okay. So, I mean, I'm sort of because it was sort of at the end of the class and we didn't go over it that much. So, I would be more inclined to study least square solutions and maybe data fitting. Okay. So, here's the idea. So, we basically want to find a straight line fit for data. So, we want to find something like y equals c plus d, and we have a bunch of points. So I don't know, let's call this T and Y. And we have a bunch of points over here like this, and they're all over the place. And we basically want to find the line which best fits the data. Okay, so the data points are going to be like Y1, T1 up to Y sub S T sub S. Okay, so these are the data points. Okay, and they're scattered all over the plane. Now, with the data points, what we do is we plug them into the equation for the line, and then we get an overdetermined system, and then we solve by least squares. So we have y1 is going to be equal to c plus dt1. y2 is going to be c plus dt2. Y sub s is equal to c plus dts. Okay? And then when we write this out in vector form, this is going to be y1, y2 up to y sub s. And that's going to be equal to 1, 1, da, 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 1, t1, t2, t sub s times cd. Okay, so when you matrix multiply everything out, you just get this, set of equations. And notice this is going to be A, this is our B here, and this is our X. Okay, so now, when you do this, you could just solve this by least squares. Okay. So I don't really need to, there's a formula for this, but I would just do it this way. I mean, if you know how to do least squares, you can just set this up and then just solve it using the least squares method. Don't have to memorize the formula, just do it. Okay. I guess that's all I have. So luckily we have a little bit of time for general questions. Maybe I can answer some specific questions too. So if you want to unmute and ask questions, please feel free.
I have a question about like what the test format is gonna be. So you said it's gonna take up like not all the time because we're gonna have time to check, but um when you said that you're gonna like test us on the earlier topics using the later topics, does that mean like those will have double weight or something?
No, what'll happen is, so basically the idea is that the test will be double the size of the midterm. Okay, the format will basically be the same, except it's going to be double the size. So each question will be worth like 20 points apiece. There'll be 10 questions. So the test will be worth, 200 points. And the type of questions or the way the questions are worded will be very similar to the way that it was done on the midterm.
Thank you.
Sorry, is that clear? I mean, I'm not,
Yeah,
I
I
don't
knew
want
what you
to,
were saying. So
yeah, I
everything's
don't,
weighted like similarly, like nothing's gonna get 2 times as weight for a different question. That's what you were saying, right?
yeah, they're all the same. They're all the same weight. And it's easier to grade that way because what I try to do is I try to grade each problem like A, B, C, and D. So A would be like 18 points and above, and B would be like 16 points and above, that kind of thing. So, if you make a calculational error, and that's just basically it, then, I don't take away like all your points because of that. So it depends on what kind of mistakes or errors are given on the problem. I mean, if it's clear, you're not quite sure about how to do the problem, then you'll get less points. But if it's clear you actually know how to do the problem, but maybe you know, there are less errors, then you get more points. So, okay, other questions? Yeah, I would say I think you guys did a pretty good job on the second midterm. Whoops, sorry about that. Hold on for a second. Maybe I'll stop sharing this. Okay. So, yeah, I think you guys did a pretty good job on the second midterm. Just make sure you write the things out clearly. And because the more clear the answers are, the more chance that you're going to get more points for your answers. Okay? And check your work too, especially on the Gaussian elimination. Okay, no other questions?
I had a question about the class in general. After the final, do we know what the grading scale is going to be in terms of like A minus? Because I know it doesn't say it on the syllabus.
So what I've been doing is I've taught this class a lot, and so usually 90 and above is either an A or an A minus. The cutoff for the A is somewhere between 92 and 93, percentage points. And B is kind of similar, 80 and above, 80 to 9, 89, that kind of thing. So it's basically a 90, 80, 70 type of scale. And it's been pretty consistent that way for many, many years. So you can actually calculate how much you have now by just taking your midterm scores and then your homework score. So you have 60% of your grade already that you can calculate. All right. Does that answer your question?
Yes, thank you.
Okay. Oh, and let me just say that I don't penalize the class for doing well. So if everybody's scoring over 90, then most people get A's and A minuses, right? So it's not like I'm gonna like take, 90 and above and partition it, on a curve or anything like that. So that's not gonna happen.
Are you posting this on your YouTube?
Yes, I will post this on my YouTube.
All right, thank you.
Okay, other questions? Okay, so if not, I might see, some of you, or hopefully most of you, on Monday to pick up your homework. And if not, I'll see you during the exam then. Okay, and like I said, if you have any questions, just feel free to send me an email or something. Okay, so I guess we'll just conclude the session. I'll stop the recording now.